In this lecture, I want to talk to you about the negative feedback amplifier, which will lead to the op amp. If you want a little history, look up the name Harold S. Black. (1927), employee at I think AT, or I guess at the time it was Bell Labs. In 1927, he invented the negative feedback amplifier while working on the transcontinental telephone system. So they had telephones that were going from one end of the country to the other, or telephone lines. And the problem was that as these cables made their way across the country over miles and miles, the signal would become weaker because of impedance in the line, and so they would have to go through another amplifier stage where the signal was amplified once again. So they would come out. You might have someone talking over here, and then it would go into an amplifier, and it would travel some distance, and then they'd put it through another amplifier, and you can imagine it would come out large here and then end up tiny over here, come out large here, and then arrive small. And the problem was that as they kept doing this from coast to coast, every time they went through another amplifier stage, distortion was added. Okay, or noise. The problem was that the amplifiers actually did not have high fidelity. So if you put a pure sine wave in, you would get that same sine wave back, but maybe you got the second harmonic. You know, if you put in something at 1,000 hertz, you might get 1,000 hertz, but then a little bit of 2,000 hertz or 3,000 hertz and other harmonics. And you can imagine that if you did that time and time again over hundreds and even thousands of miles, eventually the signal would become almost unintelligible by the time it got to the other end. So the problem was distortion in these amplifier stages. And the distortion was due to nonlinearities in the amplifier devices. Okay, in the, I'll say, transistors, they didn't have transistors then, they were vacuum tubes. All right, but they effectively, perform the same function. The transistors that we've looked at in class have nonlinearities as well, right? The MOSFET has a square law, so we know about the nonlinearities that an amplifier stage can introduce. So they were desperately in need of an amplifier that had high fidelity and was insensitive. That was the other issue, was that the parameters of these tubes would change over time and would change depending on temperature, environment, and so forth. So imagine, if you think about the MOSFET that we have studied, you have a current IDS that is dependent on the voltage, the gate source voltage, as a square law, VGS minus V threshold, quantity squared, right? Well, this may be dependent on temperature, time, right, or age. Might have unit to unit variance, right? So how could they produce an amplifier that had reliable gain? They really wanted something that just had a gain. Say, I want a gain of 10, a gain of 100. And they wanted to know that it was going to give a gain of exactly 10 or 100 all day long and every day of the year for years on end. And so this was the problem that Harold Black was working on. At the time, they were trying lots of techniques to simply linearize or improve the linearity of the amplifiers. And we've looked at linearity in our basic single transistor MOSFET amplifier, right? And our solution has been, if you want linearity, for linearity, go small signal, right? Small signal. The smaller you go, the weaker the square law dependence, and so you have something that approximates linearity. But that flies in the face of the very function that we're trying to produce, which is we want amplification. We want large signals in the end. And so what Harold Black stumbled upon or invented, and I shouldn't say stumbled because I don't know that it was just an accident. He was working diligently on it. Was something that flew in the face. It was a radical concept. Although it had been around before, they had never identified it as such. When it was identified and actually truly exposed and presented formally as a solution, it was kind of like, the first claims that the Earth was round and not flat. It was pretty significant. Well, not that significant, but it was pretty big paradigm shift. Okay, and what he suggests will become apparent here as we develop this. So, assume as our starting point, we're going to develop this negative feedback amplifier, and in the end, the negative feedback amplifier that we're going to use in our circuits will take on the form of an operational amplifier. That's the device that you can go, pull out of the parts drawer. But this negative feedback amplifier concept is much broader than that, much larger, and though it will find application specifically in operational amplifiers. So our beginning point is we're going to assume, a voltage amplifier. Okay, a voltage amplifier having very large gain, okay, voltage gain, but with significant variance, and non-trivial nonlinearity. Okay, I'm being a little bit vague, but okay. So, for example, voltage gain of maybe 10 to the 5th to 10 to the 6th. All right, that kind of voltage gain variation. So it's an order of magnitude. The gain is somewhere between 100,000 and a million. Large gain, but I can't nail it down to a specific number. Now, we've not seen gains like this from our simple amplifier circuit, but we had seen things on the order of tens to 100 volts per volt gain. And you can imagine for a moment that if you cascaded a number of these stages together, you could eventually arrive at something that has a significant gain. So we won't, at this point, look into how we produce such an amplifier, but we're going to simply represent it as a voltage-controlled voltage source. All right, and we have an input, which we'll call VI here, and it's going to be measured between these two terminals. There's no current going in here. These are just, this is a voltage that this voltage source depends on. The output of this will be we'll call it AV, A for gain, and V for voltage, the output voltage VO will be AV times VI. Now this is the 10 to the 5th to 10 to the 6th range, let's say. In addition, although I'm represented here as a constant, we want something that could actually, we were going to want to be able to deal with an amplifier that will actually have a nonlinear gain as well. So, for instance, over the range of VI that you would apply to this amplifier, it's possible that the gain might change from 10 to the 5th to 10 to the 6th as a function of VI. So, right, that would be nonlinear. So not only from amplifier to amplifier, or over temperature range, or over the life of the amplifier, would the gain vary on an order of magnitude, but it might actually vary at any given brief period of time as VI swings over its normal operating range. So that's our assumption of what we're going to start with. And this is what we start with. And the goal, okay, goal, produce this amplifier. We put in a voltage VI. Okay, I'm going to draw this as an amplifier here. And I want VO to be 10 times VI. Period. I want it 10.00 times VI, and I don't want it to vary over time, over temperature, over the life, and I don't want it to be varying over, 10%, 100%, whatever. I want it right on 10. That's what we want to do. But our limitation is all we have in our bag of parts is this amplifier that has a huge gain that varies on an order of magnitude or more basis and is actually potentially nonlinear. Can we put it to use? Before we embark on this, let me go a little further on describing this ideal amplifier that we're looking for. You know about Thevenin equivalent circuits. And so let me draw what we really
For thousands of years, roads have provided a means for safer and more efficient movement of goods and people. But as you will see in a moment, this is not always the case. While some of the roads on our list are heavily travelled thoroughfares, others are remote, winding and narrow. Whatever the case may be though, the 10 most dangerous roads in the world will likely convince you that walking isn't really that bad after all.
And there's an output port. This is our ideal amplifier. And what we have is we have an input voltage VI, and I'm going to model whatever the VI, if you were hooking on to the input port and you looked into this amplifier, you would see an input resistance of Ri. And ideally, we want Ri to be infinite. Now, why would that be? Let's say that I have some voltage source here that I'm trying to amplify, and it has some Thevenin resistance. Okay, I'll say this is VG, RG, some generator. Could be a sensor, could be a mic, whatever. And it has some, it could be a complicated circuit or sensor, but we're going to represent it as a Thevenin. So a voltage source and a resistance RG. And the voltage VI in this case is going to be a voltage division of VG, right? It'll be Ri over Ri plus Rg times Vg. Now, if I could pick any Ri in the world, why would I pick any Ri other than Ri equals infinity? Because if Ri is infinity, then I don't need to be careful about having a small value of Rg, right? For instance, even if Rg was 10 megohms, right? I'd have infinity divided by infinity plus 10 megohms, and that would still give me a voltage division equal to 1, right? In other words, VI is equal to VG, and that's what I want. Because after all, the reason I would connect VG, some sensor or some signal, to my amplifiers because I want to amplify it. So if I connect my voltage source, VG, with its Thevenin resistance to the input of my amplifier, and before I ever even get a chance to amplify it, I've attenuated it through this input voltage division, I'm just making my task of amplification even, all the more difficult. So we want an RI that is infinite. That's the ideal amplifier characteristic. Similarly, for the output, we want the output to have an output resistance of 0. Now why would that be? Let's say we connect this to some load that's going to make use of this voltage. I'll call it RL. The voltage across RL, okay, is going to be VO. We would say VO is equal to RL over RL plus RO times AV times VI. Now if I wanted an amplifier that had a gain of 10, then AV would be 10, and I don't want to lose a bunch of my voltage gain through some output voltage divider. So if RO was 10 ohms, and I was connecting a load of 10 ohms, then right there I lose 1/2 of my voltage gain. Right? I get 10 ohms load divided by 10 ohms load plus 10 ohms amplifier output resistance, and that's 1/2. So ideally, I want R out to be 0. Okay, so that's another characteristic of an ideal amplifier. And of course, I also want AV to be constant. Right? I don't want it changing on me as a function of VI or changing from unit to unit, so I want it constant. These are ideal characteristics of an amplifier. This is what I'm going for. So, in the real world, you never get to this exactly, but this is a benchmark, and we can actually approach it quite. In practice, we can get to it pretty closely under some conditions. Okay, so let's kind of table that, and maybe we'll come back and look at it after we've gone through the whole process of developing the negative feedback amplifier and the op amp. So, before we can really solve this problem, I need to introduce this idea of feedback. All right, and specifically, I want to introduce you to what's called negative feedback. I'm going to use a block diagram for showing this. Negative feedback is the idea of subtracting a portion of the output of a system, the output of a system, from that system's input. It seems kind of counterintuitive, or counterproductive, I should say, counterproductive. You take a portion of the output and you subtract it from the input that actually is the source of why you get an output in the first place. So think of your HVAC system in your home or at school. If the temperature gets too hot in the room, you actually want to reduce the heat that's going into heating the room. Right? So there's some idea there of, if you take a portion of the actual output of the system, that is the temperature of the room, and you feed that back and subtract that from the signal that is actually turning on or driving heat into this room in the first place, you can tend to regulate that temperature. Okay? So let me show this as a block diagram. So here we'll have this, we're going to represent our amplifier with the gain A. I used AV before. That's the same one. We'll just call it A here. And I have some input VI. But instead of feeding it directly into the amplifier, and here's actually my output, I'm going to feed it into a summing junction. Okay, this is a fancy symbol for just addition, or in this case it'll be subtraction. Okay, so I'll say this is my V feedback here. So this signal here, we'll call it VE, E for error, which will make sense maybe in a little bit. That's simply equal to VI minus VFB. So that symbol is just, that summation junction is just fancy for computing a difference. Now, negative feedback says you take a portion of the output and you feed it back to the input. And you subtract it from the input. So here's our minus sign that subtracts it. Now we're going to take a portion. So not all of it. So to signify a portion, we're going to put it through a block that has a gain beta. All right? And this would be less than 1. Right? The magnitude is going to be, well, it'll be less than 1. It'll be greater than 0. Okay, now this kind of looks like chicken and an egg, right? We need to write an expression for V out. So before we do that, let's just define a couple terms. A is what's called the open loop gain of the amplifier, or of this amplifier system. Okay, beta is the feedback factor. It's the fractional portion of the output that's getting fed back. So let's solve for VO. We just follow through this diagram. VO comes from this block A. So it's going to be A times whatever goes in to A, which is VE. VE is the difference between VI and V feedback. V feedback is equal to what comes out of beta block, the beta block. So it's going to be beta, and what goes into the beta block is VO. So it's V feedback is beta VO. So now we finally see we have V out is equal to A times VI minus beta VO. So it's chicken and egg, you know, and we have to isolate VO. So let's divide by A. So we'll have 1 over A VO equal VI minus beta VO, and let's collect the VOs. We have 1 over A plus beta times VO on the left is equal to VI. And so now we can write VO is equal to 1 over A plus beta times VI. Okay. Now, let's we can write it also as if I multiply through by A, it'll be A over 1 plus A beta times VI. Okay. Now, let's try something here. Suppose beta was equal to 1/10. All right. And we had A that was equal to 1. All right, let's solve for VO. Well, we'd have 1 over 1 plus 0.1. 1 over 1.1, which is approximately 0.909. Is that right? Okay, now let's suppose A was 10. We would have 1 over 1/10 plus 1/10, because beta is 1/10. So 2/10, which is 5. What if A was 100? Then we'd have, let's write it, let's use this expression here. I'm going to go to this one. It would be 100 over 1 plus 100 times 0.1, so 11. Which is 9.09. What if A was 1,000? Then it would be 1,000 over 101, which is 9.9. Yeah, 9.90, right? If A was 10,000, then we'd have 10,000 over 1,001, and the gain would be 9.99. And you see where this is going. We find that in the limit that A goes to infinity, VO goes to 10.0. But more specifically, or more generally, we can say that in the limit that A goes to infinity for VO, the gain, or the output, VO goes to, you look at this expression up here, you say that A times beta is going to swamp out the 1 in the denominator, and so it'll approach A over A beta, which reduces to 1 over beta. So the output voltage tends to be, in the limit, 1 over the feedback factor times the input voltage. And you may ask the question, where's A? Right? A is the characteristic of this amplifier. It's its gain. And yet we have rendered the gain of the amplifier insignificant to the actual input-to-output relationship, so long as A is large enough. And the condition is that A times beta must be much, much greater than 1. Okay? Or A must be much, much greater than 1 over beta. This right here is the closed loop gain. Why closed loop? Well, you go back to this diagram and you say, I've got a loop here, right? If you did not have, if that loop was not closed, in other words, if you didn't have that feedback path, so it's open, right? None of the output gets back to the input, then the gain you would have would be just A. V out is A times VI, and that's why we call that the open loop gain, right? Here we have the closed loop gain, 1 over beta, or this would be the desired, we'll say the desired closed loop gain, because the actual closed loop gain, this right here, is the actual closed loop gain. This one, I would say, is we'll say it's asymptotic. Right? It's asymptotic closed loop gain as A goes to infinity. So the condition for this to be a valid approximation of your gain, closed loop gain, is that the open loop gain of the amplifier, in other words A, must be much, much greater than the desired closed loop gain. Alright, so in our case this was 10 right here. 1 over beta was 10. We were looking for a gain of 10, so A would have to be much, much greater than 10. in order to be able to achieve this. So we'd want a gain of, at least 1,000 or more. Now think back to when I introduced this idea of negative feedback amplifier, and introduced the topic and said all we have at our disposal is this amplifier that has high gain, but it's not very controlled. It's 10 to the 5, it's 10 to the 6th, and it might even be kind of nonlinear. Well, now you can see with this negative feedback how we no longer depend heavily on the exact value of A. All we need is to have A much, much greater than the closed loop gain that we're trying to achieve. And this is kind of mysterious. It seems like some trick was played on us, but this is in fact what happens, and it's a revolutionary idea that really kind of did away with the whole approach of how people were trying to design greater linearity into their amplifiers. It actually went totally counter. We said, hey, we don't care about the linearity of this amplifier. We don't care about how controlled the gain is. We just want the gain to be really big, and with proper negative feedback, we can achieve a very tightly regulated, specified, tight tolerance closed loop gain. So now what we need to do is to apply. So we need to apply this negative feedback concept to our voltage controlled voltage source amplifier that we started out with. So remember, we had this amplifier that produced some gain AV times VI, and we didn't know what this was, but it was large, but somewhere between 10 to the 5 and 10 to the 6. So we will now draw a circuit using this amplifier and see how can we actually implement this negative feedback that we've seen in the block diagram at the schematic or circuit level.